So I'm really sorry to do this to you, but instead of having you watch one screencast for each class, I'm going to give you both of them today, and then we're going to do both of the sets of activities that go along with this internext class. Because I really want you to have an opportunity to do the hands-on stuff because I just find it to be enjoyable and interesting and helps you understand the concept. So what I'm going to talk about in this screencast is basically how we generate electricity, because electricity is sort of the go-to energy that runs our society for reasons that are going to become evident. So let's just take a look at how it is that electricity is generated in our society. So basically, electricity, as we said in our previous screencast, is energy in the form of moving electrons. It could also be ions, but in the case of societal electrical generation, it's going to be electrons. So this diagram, I think, does a really good, or GIF or GIF or whatever you call it, I think does a good job. So basically, when the switch is closed, the circuit is complete. Electrons can flow. If you notice, electrons are the red dots. They're flowing through it, and when they're flowing, the light comes on. When they're not flowing, it doesn't come on. So basically, these electrons carry energy as they travel through the wire. And when they lose energy passing through electrical devices, that energy that's carried by the electrons will then get converted into other forms, like, say, light or sound or heat. Or that's the nice thing about electricity is it's very easy to convert electricity into other forms of energy. That's why we like it. So, I mean, you can turn it into light very easily. You can turn it into sound. You can turn it into motion. You can turn it into uh, other kinds of potential energy. Basically, it's very, very easy to convert electricity into other forms of energy. It's very hard to turn other forms of energy into electricity or really into anything else, right? It's easy to turn all forms of energy into heat because the second law of thermodynamics, but it's very difficult in many cases to make a transformation of one form of energy into a desired form, right? Good luck turning sound into, say, motion, or motion into light. These are just hard things to do. But with electricity, it's just really easy and convenient to do. Another thing about electricity that's very useful is that you can release it in one place. You can manufacture in one place. You can release the energy and transform into electricity in one place, and then send it through wires at, thousands of miles away if that's what you want to do. It doesn't dissipate very quickly with distance the way other forms of energy would. So the most forms of energy follow what's called an inverse square law. Every time you double your distance, you reduce the amount of it by a factor of four. Not that it doesn't go away, but the amount that's arriving at a certain point goes away by that much. So the nice thing about electricity is we can sort of constrain it and confine it in these wires and send it to where we want it to go. So for that reason, electricity is a very, very useful form of energy that our society is basically built around. Apart from transportation, it's built around electricity. Well, how does it work? Well, basically, and my apologies to those of you in AP Physics too, because I'm greatly simplifying this, but ultimately it comes down to this. You want the electrons in a wire to have energy. You want to set them in motion, right? Electrical energy is the energy of electrons moving in a wire, right? So how do you move them? Well, one way to move them is to, does that light bulb go off when it stops? Wait. And it stops. And wait a second, I just wanted to know it stopped. No. Oh, yeah, it stopped. Aha, okay. When they start moving, the light comes on. Good. Okay, sorry, I got distracted. I'm like a dog watching a squirrel. Okay, so the idea is when you want to make electricity, you take a powerful magnet and you spin a coil of wires inside it. And as those coils of wires spin inside that magnetic field, the electrons are going to get pushed back and forth. Now, you could also spin a magnet inside a coil of wires. Six of one, half dozen the other, but usually what we do is we spin a coil of wires inside a magnetic field. And the device that does this is called a generator. It generates electricity. What it's doing is it's converting kinetic energy of a spinning wire into electrical energy of moving electrons. And it does it by passing a coil of wire through a magnetic field. Now, it's usually not a single wire like that. It's usually like, thousands of kilometers of coiled wires inside this tightly constrained field. And this is an actual, generated from a power plant. But the bottom line is we just have a very powerful magnetic field in which we're spinning coils of wires. Now, that's really how we make electricity in our society. There's a few examples where we don't do it that way, and they're important to learn about because we might need to move in that direction. But for the most part, electricity is produced by spinning coils of wires inside of magnets. Now, how do you get it to spin? Okay, how do you spin that generator? Well, usually we use a propeller-like device called a turbine. So a turbine is basically any propeller-like device that spins anytime a fluid moves against it. So a fluid, remember, can be either a gas or a liquid. So in the case of a wind turbine, when the wind blows against this propeller-like device, it spins. As it spins, it turns the generator, it spins the coil wires inside the magnets, and then electricity flows down. Electrons flow down here. A transformer is just a device that changes how much energy each electron has. So basically, when you hear high voltage, what that really means is each electron carries a lot of energy. Low voltage means you have less energy per electron. Now remember, first law of thermodynamics, you can have uh, one electron have 1,000 joules, let's say. I mean, that's a little bit ridiculous, but let's say you could. Or you can convert that into 1,000 electrons each with 1 joule. Okay, so the law of energy conservation, first law of thermodynamics, still applies, but you can do that with voltage. So when you hear, I mean, we're not going to get really into voltage, but just understand that voltage is a way of measuring how many joules of energy is present in the charge and the electrons in a wire. And so basically, all systems are going to look essentially like this. Let's just take a look at some other ones. Okay, ready? Here is another one. This is a hydroelectric power plant. What we have here is we have water stacked behind a dam. This water is at higher level than this water here, which means it has more, wait for it, gravitational potential energy. As this water loses potential energy moving from here to here, that energy must be converted. You can't destroy energy. So what happens is, in moving from here to here, that energy gets converted to kinetic energy. The water is moving faster and faster as it comes down here. What we do is we put this paddle-like, propeller-like device in this path, a turbine, and as the water flows through here, the water slows down as it interacts with this turbine. So that energy is transferred to the spinning motion of the turbine, which then turns the coils of wires inside the magnet of the generator, makes electricity. It goes into the transformer where we turn it to high voltage electricity and send it down the power lines. We like to have high voltages because the idea is each electron is going to lose some energy to heat traveling through the wire. So why not send a few electrons with a lot of energy as opposed to a lot of electrons with a little bit of energy? Okay, let's keep going. Most of the energy we have access to on our planet, though, is not in the form of wind or water. It's in the form of fossil fuels or uranium. And so these are sources of potential energy. And these vast amounts of potential energy we have access to, basically the problem is when you release chemical potential energy, when you release nuclear potential energy, it is almost 100% of the time released as heat energy. And the problem with heat energy is it's really hard to turn heat energy into anything useful. That's why we often say it was wasted as heat energy. But they figured out a very cool thing to do. It's not the smartest thing to do, but it works, okay? So here's what we do. When we release the chemical energy present in, say, coal, the chemical potential energy, we combust it, combine it with oxygen. The electrons have less energy connected to an oxygen than to a coal. And so as a result of that energy can't be destroyed, so it gets converted to heat. The heat then is used to boil water into steam. Because remember, heat is just randomly moving molecules. But when you build up steam, it makes pressure, and you can direct pressure to go which way you want. And so I take the pressure of the steam to turn this propeller-like device, and that turns my generator, and that makes my electricity. We're missing, a couple of things like a transformer here, but that's the basic idea. We release potential energy. We boil water. The boiled water makes high pressure steam, and that high pressure steam is then used to turn a turbine. That's how we make electricity in our society, almost exclusively. So let's just look at a coal plant. The coal comes in, we burn the coal, we have water that's pumping through. As the water goes through here, the high temperatures cause it to boil into high pressure steam. The steam turns the turbine. And then here I have to have a thing called a condenser, which we're going to get to in a minute. The idea is I've got to cool it back down into liquid water in order for this process to keep working. But as long as I keep the turbine spinning, then the coils of wires inside the generator keep spinning, and I keep producing electricity. At least this one included the transformer to kick up the high energy electrons and send it out on the transmission lines to your neighborhood. What about a nuclear plant? Well, you'd be surprised how similar they are. A nuclear plant is essentially the exact same process. The only difference is I'm not burning uranium by reacting with oxygen. Instead, I'm using what's called a fission chain reaction, which we'll talk about later. The idea is here is where my nuclear material is undergoing its nuclear chain reaction. It generates heat because I'm releasing nuclear potential energy. Just like when I release chemical potential energy by burning coal, it got converted to heat. When I release nuclear potential energy through the process of fission, it generates heat. Now, the difference is this is radioactive, so I got to be a little bit careful. So we have as a separate system, we pump a liquid through here to collect this heat energy, and I pump this heat energy through here. Now, notice this is a closed system, so the material that's going through the core is contained. But the rest of it's the same. I put water in here. The high temperature here boils that water, which makes steam. The steam turns the turbine. The turbine turns the generator. We're missing our transformer here, but you know it's there. And then I have to turn it back down. I have to condense it back down to a liquid and start the process over again. It's the same thing, right? It always works this way. Now, the problem is this is a very low efficiency way of generating electricity because we're using heat energy, and that means lots of things are getting hot. We don't want anything to get hot. What we want is electricity. We just like take the chemical potential energy here and turn it into electrical energy here. But that's not what happens. I generate all of this heat. These pipes get hot. The turbine gets hot. I have to turn this water from steam back down into liquid water, so the water that's doing that gets hot. There's all this excess heat. In fact, it turns out only about 30% of the energy that comes in as chemical potential energy leaves as electrical energy. 70% of it just goes to heating up all the different components of the power plant. That's very typical. So what that means is we have a 30% efficiency. Think about that. We waste 70% of the energy on our planet, and it's non-renewable. We don't get more of it. We throw away 70% of all of our energy. Guys, we're too smart to be doing this. But that's what we started doing this 150 years ago, so we just keep doing it because it's the easiest thing to do. It needs to be changed. Now, another problem we have that lowers our efficiency and also causes another problem is that in order to keep this turbine spinning, you can't have the same amount of pressure on both sides, right? If you have the same amount of pressure on both sides, it's pushed equally in both directions, it's not going to spin. It needs to be pushed harder this way and not as hard the opposite way. So this is coming out as high pressure steam, which is hot. That means on this side, it has to be cooler, otherwise it won't work. So how do I make it cold? What I do is you'll notice that electrical generation plants are almost always built near a body of water. Not almost, they are always built near a body of water because we need that water to condense the water steam back into liquid water. Without it, it won't work. The turbine will stop spinning because the pressure will be the same on both sides. We have to have this condenser to condense the steam back into liquid water to maintain the pressure differential between the incoming steam and the outgoing steam. Okay, and what that means then is we basically pump cold water into here. It absorbs a lot of the heat energy here. And then we don't want this heat energy. So we just like basically sit into these weird looking towers that you see. And when you see these towers, you probably think, oh, that means a nuclear power plant. It doesn't necessarily mean a nuclear power plant. It just means a power plant. These are just cooling towers. And they always see that there's steam coming out of them. It's not pollution. It's just steam. Now, when I say it's not pollution, there's a thing called thermal pollution. This waste heat that we're talking about can be a problem. But apart from that, we're throwing away energy. Now, there's a concept called cogeneration. This is a new idea, which is like, wait a second, why don't I take some of this water here instead of just like, letting it cool itself down to steam? Why don't I pump that into town and use it to like warm up municipal buildings and stuff like that? So that's one thing that can be done. But for the most part, we just waste the energy. Now, last topic for today, promise, is called thermal pollution. The idea is this: when I put in a cooling tower, I'm taking water out of the river. I'm using it to turn the high pressure steam on one side of the turbine back down to liquid water, and then it comes back out. I have to cool it down as much as I can, but still, I got to keep the system moving, so I can't let that water reside there too long. So I got to let it flow out. And what happens is when it comes out, it can be 10 degrees warmer than when it comes in. So the upstream water comes in, let's just say at 15 degrees, and then it comes out at 25 degrees, right? And we call this thermal pollution. You might think, well, what's the big deal? So the water's warm. That's not a big deal. Well, it turns out it is a big deal, and here's why. Because all gases are less soluble in hot water than they are in cold water. And so because what keeps it in there is pressure. And when you heat things up, they're at higher pressure, they get pushed out of the water. So look at this curve here. So here's temperature. As the temperature of the water gets warmer, you notice the amount of oxygen we can dissolve in it gets smaller and smaller and smaller. Uh, and so why is that a problem? Well, because there's a lot of things that live in the river and they need to breathe oxygen. And when you heat up the water, they can't. So what we find is above the power plant, remember this is true for coal or nuclear, what we find is the water temperatures are fairly cold. That means we can keep it well oxygenated. We have good DO levels. The fish and invertebrates and other oxygen breathing organisms are healthy. Okay. I dump in the warm water now from the power plant, and now the water is really warm. When the water is warm, my dissolved oxygen levels are low. There's not enough to support the fish, so the fish die, and then the dead fish serve as BOD, which drops the DO further downstream. So it can be a real problem. So again, this is one of those things we have to figure out in our society, that it's an unintended consequence, which is what this class is. I mean, we can almost call it the class of unintended consequences. Anyway, so there you go. I believe that's the last slide. Yep. So that's it for how we generate electricity. And so for the rest of the year, we're just going to talk about like what are our options here? What are other ways of generating electricity? How are we doing it? And what are the consequences of it? And what are some of the other ways of doing it? Because your generation really needs to figure out a better strategy, because my generation and my father's generation and my grandfather's generation, they just did it all wrong. And my generation did it all wrong. We got to find a better way. And that's what your generation is going to do. But you know what? Your generation, you're starting out having environmental science in high school. They did not offer that when I was, when my wife was in college, they didn't offer it. Okay. So we now are at a point in our development as a society that we understand these issues. We can teach people who are your age, really smart people your age, and you can go forth and implement new ideas and save the world from the destructive practices of my generation and my predecessor's generation. See you guys in a couple days.